Hi everybody, I'm Zaven. I want to thank Paul and Nico for asking me to give this presentation. By all rights, Anna Watts would be the one doing it. Unfortunately, she couldn't be here, but she graciously provided a lot of content. Of course, any errors or foolish statements are my own. Where is
the right arrow?
We're looking at a PDF?
Yeah.
Okay, so never mind, there were animations. We've heard several mentions already today about the transparent state, what makes it special, and the interest that exists out there beyond the X-ray astrophysics community in resolving this question, which has been an open question for something like 8 years since neutron stars were first proposed. Of course, the key is that we can study ultra-dense matter densities higher than those of within the atomic nucleus at high temperatures and high interaction energies with experiments of the kind that Andrew described this morning in accelerator facilities. But to understand what happens to that matter at cold temperatures and very high densities, the only accessible place, not very accessible at that, is neutron stars, the cores of neutron stars. Fortunately for us, thanks to some nifty properties of general relativity, it's possible to map observable quantities like the mass and radius of neutron stars, especially a collection of neutron stars, to the pressure density relationship, which is the equation of state for dense matter. And that is a unique mapping, provided that we can make these measurements over a range of neutron star masses. So the colored curves here represent doing the inverse of what that blue arrow is, using an assumed equation of state to derive the mass-radius relationship that will be seen in a compact star. And that's what these curves represent. If we can actually pin down measurements, small blobs, small error circles in the mass-radius plane through observation, we can translate that back into our knowledge of the equation of state. In our STROBE-X study proposal, we claimed that we would do that. This is a figure from that proposal. So how do we intend to actually accomplish this again? There have been constraints from past observatories using multiple different techniques. And this very vague outline labeled RXDE attempts to show an envelope in which some of those measurements were made. It's obviously not very constraining. We have also independent measurements of masses from radio pulsar timing. Those give horizontal bands in this plot. And except for the very, very highest mass measurements, they're not very constraining either. And theorists are very clever in how they can tweak their model parameters to accommodate the new measurements of very high masses. So in some sense, they become even less constraining over time. So ideally, we'd love to have joint mass and radius measurements for individual objects, enough of them spanning a range of masses that we can really identify which of these curves is ruled out and which remain viable. So what are some of the approaches at our disposal? We have the possibility of modeling X-ray light curves. This was brought up also this morning in the context of treating traditional X-ray pulsars and high-mass X-ray light curves. We can apply that same technique to multiple different classes of modulations that arise due to the rotation of neutron stars. We can look at rotation-powered pulsars, preferably millisecond pulsars, because the rotation, the Doppler shifted emission, the Doppler boosted emission, both of those effects, spectroscopic and photometric Doppler shifting and Doppler boosting, can play an important role in helping us figure out the mass radius of the neutron star. We can apply the same technique to accretion power millisecond pulsars, those that show persistent pulsations at least during an outburst. And we can, in principle, apply the technique again to burst oscillations. So these are very short-lived oscillations that I believe Lawrence this morning mentioned that we see during X-ray bursts. So I'll talk a little bit more about that in the next few slides. X-ray bursts offer an opportunity through spectroscopy in looking at both the whole surface emission at the end of a burst, where especially if there's, for example, photospheric radius expansion, that when the atmosphere falls back, when the outer layers fall back onto the star, and the temperature has become uniform all over the surface, we can do a simple black body height calculation for the continuum spectrum to estimate the size of the star. We can also look for lines and absorption edges, and I'll say a little bit about those things. Each of these techniques has its own systematic effects and its own sensitivities to calibration uncertainty. And we'll talk about those. Thermal evolution, again, touched on this morning. Cooling curves for young neutron stars. Thermal conductivity is a sensitive measure, a sensitive probe onto what the contents of the neutron star are in pure composition. And post-accretion cooling tells us, at a minimum, about the nature of the crust, and should validate our assumptions about the interior are correct. Capability of the interior to be a good heat sink. Finally, astroseismology of neutron stars, offers a very, very powerful probe of the stellar. But as I said, these all are subject to both modeling uncertainty and calibration. As the person who's been defending NICER's science objectives for many years, I'm sensitive to the argument that modeling uncertainties make making measurements dubious. That this is an argument that we've been battling a long time. Every time we say, here's a new approach, people say, but there are too many modeling uncertainties, and the theory is not well enough established to allow you to derive reasonable outcomes from sensitive measurements. And my only response to that is, does that mean we stop making measurements? That doesn't make any sense. If you have theoretical uncertainties, as David just said a few minutes ago, the answer is more data, broader data, try to reduce the parameter space and look at different types of objects, use multiple approaches on the same object to try to at least determine the systematic effects or distorted results or biased results. Anyway, the key here for STROBE-X is that several of these, the ones in blue, represent short duration phenomena. And when you have a persistent pulsation, as we do with rotation powered and accretion powered millisecond pulsars, you can substitute collecting area. If you have a lack of collecting area, you can make up for it by having deep exposures. The number of photons you collect ultimately drives the signal-to-noise ratio of your light curves, which ultimately drives your ability to model them and to derive mass radius constraints. So if you need more photons and you have a persistent signal, you can always spend more time. But if you don't have a persistent signal, if you're looking at an X-ray burst or a burst oscillation, you really need area. There's no substitute for collecting area. Another leaking phenomenon is oscillation, whole body oscillations of the star. So for astroseismology and these other things in blue, we would need collecting area. And I think that's where STROBE-X will really shine. This is the effective area curve that collection that we plotted in the proposal. Relative to NICER, the XRCA on STROBE-X will offer something like a factor of 16 to 20 more collecting area. And if you're thinking, as I typically do for rotation-powered pulsars, our best case millisecond pulsar comes in at about 1 count per second for NICER. We're looking for 1 million photons to achieve a signal-to-noise ratio of 1,000. We're talking about a megasecond of time. If we have 20 times the collecting area, we can get the same signal-to-noise ratio of 50 kiloseconds. The difference between 50 kiloseconds exposure and a megasecond exposure is enormous in terms of the efficiency of the pulsar. So this factor, 15 to 20, is a game changer. That factor of 15 to 20, in case you don't remember the configuration that the sort of baseline configuration that we put in the proposal, relative to NICER comes from having approximately 2.5 times as many detectors versus having each of those optical detector combinations in this very modular architecture having about 7 times the effective area as NICER. So there are some impacts related to net time and pileup relative to NICER that we have to still consider the XRCA on STROBE-X. But there's a pretty good balance there in terms of the number of objects and the total effect there. This animation won't play on PDF, but I can show it to you on my laptop later if you'd like to see it. This basically is a nice encapsulation of the lecture model technique. You've got a star, imagine in the weak gravity limit, something like a beach ball with a hotspot on it. On the one hand, as it spins, the hotspot comes into view and the hotspot goes out of view. When it's out of view, it's out of view. You get 0 flux in your light curve. On the other hand, if you have a strongly self-gravitating object like a neutron star with a hotspot on it, as the neutron star spins the hotspot out of what would have been backspin towards the backside of the star, out of your sight line, the gravitational light bending for surface emission from the backside wraps some of that emission around the star and brings it in the forward direction toward the observer. You no longer get 0 emission. You get a significant distortion of the shape of the light curve due to Doppler boosting and gravitational light bending and gravitational redshift on the gravitating surface of the star. And it is possible, it's been shown to not very high precision, but this is NICER's key science, it's what we're pursuing now, that you can model the light curve to recover the mass to radius ratio at a minimum, and in some cases the masses and radii separately for neutron stars. I'm showing, sorry about the overlapping text and stuff. This is the table. This table shows NICER's top 5 light curve modeling targets. J0437 is our poster child. It comes in at just over 1 count per second, and its geometry is very well known. I'll explain why that's important on the next slide. 0437 is the brightest known rotation power millisecond pulsar. It's very nearby. It's only about 150 parsecs away. Its distance is focused on exquisite precision. That turns out not to be relevant for this analysis, but nevertheless, it's good to know. It's a factor of 4 brighter than the next brightest known rotation power millisecond pulsar, and every other is dimmer than that. So what STROBE-X offers for this analysis is that it brings into play, we're no longer relying on the tail of the distribution of these rotation power millisecond pulsar. STROBE-X brings into play play, and the circle is meant to extend down a little further. The much larger population of more common dimmer rotation particles and pulsars for this vector model. The key to light curve modeling, whether you're talking about rotation powered or accretion powered or burst oscillation type modulations, is you have to have a good handle on at least three things. One is the geometry. You have to know where the hotspot is on the surface and where the viewing, where the observer is observing the star, what co-latitude on the star surface. This is something that we try to get for rotation power pulsars from radio polarization measurements and also by fitting gamma ray light curves. We have a pretty good idea for our key targets what their geometries are, but that is independent information that we use when it's available. You also have to have good ray tracing models that account for the rotation of the star and its possible obliqueness due to rotation. This is work that Sharon Morsink and Fred Lamb and Paul Miller and their collaborators and students have done for many years. It's been pretty well established and just in the last year validated against other calculations that have been done by Atrios Psaltis and Ferrial-Ozel and so on. And so we think we've now got a very robust ability to do this ray tracing. And finally, you need to have a good understanding of the atmosphere through which the X-ray emission is traversing. Again, this is pretty well understood, although there is potential for systematic uncertainties, systematic effects and biases coming in due to neutral fraction, muted fractions of that are not ionized in the atmosphere. Some compositional effects like helium being present instead of hydrogen, which is not expected, but may be going on. All right, so once you have those ingredients in place and you have the effective area that STROBE-X offers, you begin to open up the possibility of doing light curve modeling with burst oscillation. That's interesting because as a group, the accreting pulsars are spinning much faster than the rotation pulsars, and the higher spin brings in Doppler effects that break some degeneracy to the mass radius impacts on the light curve. And you're more likely to separately get mass and radius for a single object through burst oscillation modeling than you are through the rotation powered millisecond pulsars. Unfortunately, a whole new set of systematics comes into play with burst oscillations. First of all, they drift with time, their frequency changes with time, so it's not clear that the burst oscillation frequency is really the underlying frequency of the neutron star. These red patches show that changing the burst oscillation frequency, in some cases they look pretty stable, in other cases they do not. That's work by Anna Student. And then there are lots of questions about why the burst oscillations are as persistent as they are. Lawrence this morning mentioned flame propagation models. At first blush, theory would suggest that the flame front from an accretion-powered thermonuclear burst should engulf the star very rapidly. But instead, we see over tens of seconds or longer the temperature anisotropy that is causing the burst oscillation, the X-ray flux modulation with approximately the spin of the star to last longer than we expect. And so there are theoretical uncertainties about why this happens. And if you don't have a good sense of the size of the spot that you're trying to model, it becomes much harder to believe your light curve modeling result. And so some of Anna's group's work now, a significant amount of their work involves understanding emission and flame spreading, the effects of the Coriolis force and the spin of the star in keeping the temperature anisotropy from spreading across the surface and the effects of convection.
I'm going to wrap up. Just to
Touch on the other subjects, I've got a couple of summary plots here from a review by Ferriol. This shows light curve modeling results for accreting millisecond pulsars from RxTV through about 2012. As you can see, the blue, solid blue and dashed blue contours in the master radius plane refer to the same object in the same data set as analyzed by different groups. And so there are clearly differences of opinion and models that need to be reconciled. This is the kind of thing where model uncertainty is more important than the data quality. But again, if you have higher signal-to-noise data and you can look at individual pulses instead of having to collapse them all into one standard pulse, just to build up the signal-to-noise, you stand a better chance of ruling out some systematic effects. Here's another summary plot of mass and radius constraints from the continuum spectroscopy of X-ray bursts. Again, lots of controversy here. Probably people in the room understand the controversies better than I do, but mostly having to do with stacking spectrum from multiple bursts. So again, if you have a factor of 20 or more increase in collecting area, you don't have to do so much stacking. You can do your spectroscopy on a smaller number of bursts from a smaller variety of objects and reassure yourself that the uncertainties are less important. Finally, this is the second to the last slide, looking at edges and lines from bursts. This is courtesy of Lawrence. In a super expansion burst, one can hope to see edges both at the absorption edges, both when the expanding photosphere is hundreds of kilometers off the surface where the gravitational redshift is minimal, and then again when it collapses back down to the surface, and you can see measure the displacement of the edge and get a direct measurement of the master radius ratio of the star. Finally, oscillation modes. This is a plot from Latimer and Prakash's review in 2007. The orange bands represent their mode identifications and interpretations of oscillations seen in SGR bursts, magnetar flares. And if you've identified the modes properly and can map them to a mass radius model, a mode model, then you can make these constraints. But again, those are highly uncertain things, and these are very, very short-lived phenomena. So I think this is somewhere where STROBE-X can really shine if these kinds of oscillations are kicked off by relatively low energy events, not only superbursts, but perhaps photospheric radius expansion bursts, intermediate duration bursts, or even regular X-ray bursts. And you can see these high-frequency flux modulations that offers an interesting capability that doesn't exist for now. Thank you.